Good morning, one and all. My name is V. Abhijit Kumar. My roll number is 24951A6602. I'm studying in CSE AI and ML, that is Computer Science and Engineering, with the specialization of Artificial Intelligence and Machine Learning, 4th semester, Institute of Aeronautical Engineering. In this tech talk video of the subject of Applied Artificial Intelligence, that is AAI, the topic I've chose and to talk about is Semantic maps for knowledge graph, a semantic-based summarization approach. So let's go to the topic. Now let's go through the contents of this presentation. In the first place, introduction to knowledge graphs. I'm going to explain about understanding structured knowledge representation in AI systems. And after that, I'm going to explain the need for semantic-based summarization. I'll explain why traditional approaches fall short with large-scale graphs. Then after that, I'm going to explain about concept of semantic maps. I'm going to explain about reduced representations that preserve meaning. And after that, I'll go to the slide semantic maps for KG summarization. I'm going to explain core methodology and principles over there. Then after that, we'll go to the slide AI techniques in semantic mapping. I'm going to explain about machine learning and graph analysis methods. Then after that, in the final place, I'm going to explain about applications of this concept in applied AI, and I'm going to conclude the topic. That is, I'm going to explain about real world use cases, implementations, and an overall summary. Now let's go through introduction to knowledge graphs. Knowledge graphs have become fundamental structures for representing and organizing structured knowledge in modern AI systems. They encode entities as nodes and relationships as edges, creating rich semantic networks that capture real-world information. In here, we have to discuss about three main aspects. First is scale challenge. Large-scale knowledge graphs contain millions of entities and billions of relationships, making direct computational processing inefficient. Complexity issue. The interconnected nature creates massive complexity that hinders reasoning, interpretation, and practical application. For this, the solution approach is that the semantic-based summarization and intelligent mapping techniques extract meaningful knowledge whilst preserving the context. Hence, this is the introduction to knowledge graphs. Now let's go through the need for semantic-based approach. The first of all, we have to genuinely discuss about the growing complexity problem. Today, the knowledge graphs expand continuously as the new data streams in from various sources. This growth definitely represents significant challenges for AI systems attempting to leverage the encoded knowledge effectively. Here, four important aspects. First aspect is that the excessive nodes and relations dramatically increase computational costs. Not all information carries equal importance for specific reasoning tasks. Full graph traversal becomes impractical for real-time applications. Memory constraints limit the deployment of large graphs in production systems. Semantic summarization hence addresses these challenges by focusing on meaning and relevance rather than preserving raw structural completeness. Hence, this is the justification for the need of semantic-based approach. Now let's discuss about the concept of semantic maps. Semantic maps are intelligently reduced representations of knowledge graphs that maintain semantic fidelity whilst eliminating redundancy. Here, semantic maps have five qualities, five importantly, immensely notable qualities. First, that they have selective preservations. That is, they identify and retain important entities based on relevance, centrality, and semantic significance within the graph structure. Next, they have relationship integrity. They preserve critical semantic relationships that encode meaningful connections between entities. They have redundancy elimination. That is, they remove redundant nodes and less informative edges that don't contribute substantially to semantic understanding. They have structural consistency, that is, they maintain interpretability and coherent structure, ensuring that the map remains navigatable and meaningful. Navigatable or navigable, both are the same. And they have high level abstraction. This is the most genuine this is the most genuine quality of semantic maps. They function as abstract representations that enable efficient AI reasoning without information overload. Hence, this is the concept of semantic maps. Now let's discuss about semantic maps for knowledge graph summarization. Here firstly we have to discuss about three key principles. First one is relevance-based selection. The entities are identified and ranked based on connectivity, semantic centrality, and domain importance. The next key principle is semantic preservation. Critical relations are retained to ensure that the essential meaning and context remain intact. Hierarchy guided abstraction. The concept hierarchies and similarity metrics guide the summarization process. This results in such a map, a semantic map that represents the essence of the original knowledge graph, a distilled version that captures the most semantically significant elements. This enables efficient understanding and reasoning without sacrificing semantic context. The map serves as a navigable, interpretable abstraction that AI systems can process quickly whilst maintaining the depth needed for meaningful insights. Here we have a key advantage. The semantic maps reduce graph size by 60 to 90%, almost 60 to 90%, whilst retaining over 85% of semantic information for downstream AI tasks. Hence, this is the concept of semantic maps implemented for knowledge graph summarization. Now let's discuss about AI techniques used in semantic mapping. Multiple AI methodologies work in concert to create effective semantic maps from complex knowledge graphs. First of all, here we have five techniques, five of the most important techniques to discuss about. First technique is natural language processing technique. It helps in extracting and interpreting entity meanings from textual descriptions, enabling semantic understanding of node content. Graph embeddings. It transforms graph structures into continuous vector spaces, capturing semantic relationships in distributed representations. Machine learning, the most important one. It learns relevance scoring functions to automatically identify important entities and relationships from patterns. Clustering and abstractions. Groups It groups similar entities and creates hierarchical abstractions that simplify complex graph structures. And ontology-based reasoning. It ensures semantic consistency during formal ontologies that define domain concepts and their interrelationships. Hence, these are the AI techniques used in semantic mapping. Now let's discuss about applied AI applications. Here we have five of the most important applications, five of the most dominant applications in today's world. First of all, it is applied in explainable AI systems. Semantic maps provide interpretable knowledge structures that make AI decision making transparent and understandable. Knowledge-based question and answer system. It helps in knowledge-based questioning and answering. That is, it enables efficient question answering by providing concise, relevant knowledge subgraphs for query resolution. It is used in intelligent search and recommendations because power semantic engines and recommendation systems with distilled knowledge representations are genuinely applicable over there. And it is used in decision support systems. That is, it provides executives and analysis with high-level knowledge abstractions for informed decision making. It is applied in domain-specific AI assistance. It enables specialized AI agents to reasoning to efficient reasoning over domain knowledge without computational bottlenecks. Hence, finally, after all this, I would like to conclude this topic. That hence, semantic maps for knowledge graphs provide an effective semantic-based summarization approach that reduces complexity whilst preserving meaningful knowledge. By leveraging applied artificial intelligence techniques such as semantic analysis, graph learning, and abstraction, this approach enables efficient reasoning, improved interpretability, and scalable knowledge utilization in modern AI systems. This result is intelligent knowledge representation that bridges the gap between comprehensive graphs and practical AI applications. And finally, I to the respected professor who has given me this wonderful opportunity to speak upon this wonderful topic. Thank you.